Good morning, champs. Today we finally understand Laurent series. Not just formulas, not just tricks, but a clear method you can always follow. And especially how Laurent relates to Taylor, how to compute it, and where the circle comes from. Let's begin with something we already know, Taylor series. A Taylor series writes a function using powers of z minus a. So if we expand around a point A, everything is written in terms of z minus a. For example, z minus a squared, z minus a cubed, and so on. Taylor series only use non-negative powers. Now comes the key idea. Sometimes Taylor is not enough. If the function has a singularity, Taylor fails. So we extend it. Laurent series allow negative powers. So now we can have both positive and negative powers. A good way to remember this is Taylor goes forward, Laurent goes forward and backward. Now, before we do an example, here is the general procedure. Step 1, find the center. If we expand around a point A, then everything must be written in powers of z minus a. Step 2, rewrite the function. We force everything into z minus a. Step 3, use a known series. Most of the time, this will be the geometric series. Step 4, read the condition of the series. This condition tells us where the expansion works. And this is exactly where the circle comes from. Step 5, write the final result. If you follow these steps, you can solve any Laurent problem. Now let's do an example. We take the function 1 over z, and we expand around the point a equals 2. Since the center is 2, our building block is z minus 2. So we rewrite z as z minus 2 plus 2. This gives 1 over z equals 1 over z minus 2 plus 2. This step is not random. We are forcing the function to use z minus 2. Now we use the geometric series. First, we look inside the circle. We factor out the 2. This gives 1/2 times 1 over 1 plus z minus 2 divided by 2. Now this matches the geometric series. So we expand. We get a series in powers of z minus 2. Only positive powers appear. So this is a Taylor series. Now we ask where this works. The geometric series only works if the absolute value of w is less than 1. Here, w is z minus 2 divided by 2. So we need the absolute value of z minus 2 divided by 2 to be less than 1. That gives absolute value of z minus 2 less than 2. This is the circle. It means all points whose distance from 2 is less than 2. So inside this circle, the Taylor series works. Now we look outside the circle. The previous expansion does not work there. So we rewrite the function differently. We factor out z minus 2 instead of 2. Now we get 1 over z minus 2 times 1 over 1 plus 2 divided by z minus 2. Again, we use the geometric series. Now w is 2 divided by z minus 2. So we expand. Now we get negative powers. This is a Laurent series. Now we check where this works. We need the absolute value of 2 divided by z minus 2 to be less than 1. That gives absolute value of z minus 2 greater than 2. So this works outside the circle. Now we have the full picture. Same function, same center, but two different regions. Inside the circle, we get a Taylor series. Outside the circle, we get a Laurent series. And the circle is not chosen randomly. It comes from the condition of the geometric series. A good way to remember this is the center tells you what to write, and the condition tells you where it works. And that is the idea behind Laurent series.